Hi. The SZ or Sunyaev-Zeldovich effect is the observed distortion of the cosmic microwave background spectrum used to detect the disturbance of density in the universe. Using the SZ effect, dense clusters of galaxies can be discovered independent of their redshift. In this video, we'll discuss the theory of the Sunyaev-Zeldovich effect and results for some of the clusters, concluding with the prospects from the latest research being conducted to understand the SZ effect. Let's begin. As we discussed in an earlier video, the cosmic microwave background is one of the most fascinating remnants of the Big Bang. It is the oldest light we can observe in the universe, dating back to just 380,000 years after the universe came into existence. You can imagine this faint glow to be like static caught by a sensitive radio dish. As measured by the COBE satellite, the CMB is almost completely uniform with an almost constant temperature over the whole sky. This, for instance, is the picture of the entire sky where each pixel is color-coded by its temperature in the range from 0 to 4 Kelvin. And as you can see, it is pretty constant. But it is not completely constant. Another set of instruments called the differential microwave radiometers on board the COBE satellite measured the tiny temperature variations between the hot and cold spots on an angular scale of around 7 degrees on the sky. That is represented by this picture here. There are tiny fluctuations or ripples in the temperature of the CMB at the level of just 1 part in 100,000. For reference, consider that if the Earth's surface were smooth to 1 part in 100,000, the highest mountain would be just 100 meters tall. This patchy distribution of very small fluctuations in the temperature of the CMB implies that if our eyes were sensitive to microwaves, we would see this pattern in the sky. The SZ effect causes a change in the apparent brightness of the cosmic microwave background radiation towards a cluster of galaxies or any other reservoir of hot plasma. Recall that clusters of galaxies contain hot X-ray emitting charged gas. So when the low energy CMB photons collide with the high energy electrons of the plasma, they receive an average boost of energy. This phenomena is known as inverse Compton scattering. The Sunyaev-Zeldovich effect was predicted by Rashid Sunyaev and Yakov Zeldovich to describe the anisotropies in the CMB spectrum. Measurements of the SZ effect provides different information about cluster properties relative to X-ray imaging data. On the other hand, combining X-ray and SZ data leads to new insights into the structure of gas in the clusters. The effect is redshift independent, which makes it a unique probe of the structure of the universe on the largest scales. The SZ effect is most apparent when observing galaxy clusters. Analysis of CMB data at higher angular resolution, that is greater detail, requires taking into account the Sunyaev-Zeldovich effect. The SZ effect can be divided into different types. Thermal effects, where the CMB photon interacts with the electrons that have high energies due to their temperature. The kinematic effects, which are a second-order effect where the CMB photons interact with electrons having high energies due to their bulk motion, and polarization. The SZ effect is very important from an astrophysical and cosmological point of view. It can help determine the value of the Hubble constant, determine the location of new galaxy clusters, and of course, the structure and mass of clusters. Since the SZ effect is a scattering effect, its magnitude is independent of redshift, which means that clusters at high redshift can be detected just as easily as their counterparts at low redshift. The distortion of the CMB resulting from a large number of high-energy electrons is known as the thermal Sunyaev-Zeldovich effect. By comparing the SZ effect and X-ray emission data, the thermal structure of the cluster can be studied. If it is known how the temperature varies as a function of radius in a cluster, the SZ data can be used to determine the baryonic mass of the cluster along the line of sight. Comparing SZ and X-ray data can also be used to determine the Hubble constant using the angular diameter distance of the cluster. These thermal distortions can also be measured in superclusters and in gases in the local group, although they are not easy to detect. In superclusters, the effect is not strong, usually less than 8 microkelvin, but with precise equipment, measuring this distortion can throw new light on the formation of large-scale structures. Gases in the local group may also cause anisotropies in the CMB due to the thermal Sunyaev-Zeldovich effect, which must be taken into account when measuring the CMB for certain angular scales. The kinematic Sunyaev-Zeldovich effect is caused when a galaxy cluster is moving relative to the Hubble flow, or in other words, with respect to the rest frame of the CMB radiation. This bulk motion would cause scattering of CMB photons such that the entire blackbody curve is shifted such that the temperature of the CMB appears different in the direction of the cluster. This is the kinematic Sunyaev-Zeldovich effect, essentially just the Doppler shift of the photon frequency caused by the motion of the cluster. The magnitude of the effect is proportional to both the line of sight velocity and mass of electrons in the galaxy. Unfortunately, for a large galaxy cluster, the kinematic Sunyaev-Zeldovich effect is predicted to be on the order of 20 times weaker than the thermal SZ effect, which is already relatively small as shown here. Thus, when looking at individual galaxy clusters, astronomers have only been able to put upper limits on the distortions due to the kinematic SZ effect simply due to the difficulty of observing such a weak signal. The kinematic SZ effect provides a method for calculating the peculiar velocity as shown by this equation. Here, Vp is the peculiar velocity and tau is the optical depth, respectively. In order to use this equation, the thermal and kinematic effects need to be separated. The effect is relatively weak for most galaxy clusters, but gravitational lensing can be used along with the peculiar velocity to determine other velocity components for a given galaxy cluster. These kinematic effects can be used to determine the Hubble constant and the properties of clusters. Sunyaev-Zeldovich research is focused on modeling how the effect is generated by the plasma in galaxy clusters and on using the effect to estimate cosmological parameters such as Hubble constant. Hydrodynamic simulations of structure formation are being studied to gain data on thermal and kinetic effects in the theory. Observations are difficult due to the small amplitude of the effect and the confusion with experimental error and other sources of fluctuations in the CMB temperature. To distinguish the SZ effect due to galaxy clusters from ordinary density perturbations, both the spectral dependence and the spatial dependence of fluctuations in the cosmic microwave background are used. A factor which facilitates high redshift cluster detection is the angular scale versus redshift relation. It changes very little between redshifts of 0.3 and 2, which means that clusters in this redshift range have similar angular size on the sky. The use of surveys of clusters detected by their Sunyaev-Zeldovich data for the determination of cosmological parameters has been well demonstrated by several authors, including Barbosa et al. 1996. This might help in understanding the dynamics of dark energy in surveys. Researchers from the Cambridge Radio Astronomy Group and the Owens Valley Radio Observatory were the first ones to detect the Sunyaev-Zeldovich effect from clusters of galaxies back in the year 1984. In 1987, the Cosmic Background Explorer satellite, or COBE, observed the CMB and provided more accurate data for anisotropies in the CMB, allowing for better analysis of the SZ effect. 10 years later, the Rayleigh telescope was used to image a cluster of galaxies in the SZ effect for the first time. Instruments built specifically to study the effect includes the Sunyaev-Zeldovich camera on the Atacama Pathfinder experiment and the Sunyaev-Zeldovich array, both of which saw their first light in 2005. In the year 2012, the Atacama Cosmology Telescope performed the first statistical detection of the kinematic SZ effect. In 2012, for the first time, the kinematic SZ effect was detected in an individual object. The South Pole Telescope has been used since 2015 to discover 450 galaxy clusters using the SZ effect. Recent experiments, such as the Olympo balloon-borne telescope, try to collect data in specific frequency bands and specific regions of the sky in order to pinpoint the SZ effect and give a more accurate map of certain regions of the sky. The Sunyaev-Zeldovich effect has been and will continue to be an important tool in discovering galaxy clusters near and far. I hope you learned something new from this short discussion on the SZ effect. Please do like, share, and subscribe to our channel and share our content with other astronomy enthusiasts. I will see you next week. Until then, take care.